I'm Sabeta Matsumoto. In this video, we're going to take a look at how torques act on extended bodies. First, we'll look at what happens when the axis of rotation is fixed. Then we'll have a look at what happens when that axis is accelerating. Imagine we just have a point particle of mass m that's located at some distance r from our origin and is currently traveling at velocity v. The angular momentum for this particle is just going to be r cross p. And if we want to find the torque in this system, the torque is the rate of change of angular momentum, which is r dot cross p plus r cross p dot. The first term here is 0 because r dot, the velocity, is parallel to the momentum. And we end up with r cross the rate of change of momentum. And this is just equal to r cross the force acting on particle m. Imagine now we have an extended body that's rotating at angular velocity omega about this origin. Again, we're going to look at what happens to an infinitesimal mass element that's located at position ri from the origin. So here, our angular momentum, which we worked at before, is just the sum on I of ri cross pi. Again, because this is rotating about a fixed origin, we can convert rotational motion into a tangential velocity of this particle, which gives us Ri cross Mi Ri omega. And we can recombine these terms, and this gives us a sum on I of Mi Ri squared times omega vector, which is equal to the moment of inertia about this axis times the vector omega. The torque on this object is just the rate of change of angular momentum, which is I times the angular acceleration of this system. So from Noether's theorem, we looked at systems that have rotational symmetry. So, for instance, systems that don't have any external torques. And rotational symmetry is enough to tell us that the angular momentum in a system is conserved. Imagine now that we have a much more complicated system. What happens when the center of rotation isn't fixed? This can happen with some extended body, but I'm just going to draw a simplified setup just so you understand the geometry of the situation. Imagine we've got two particles, m1, which is located at distance r1 from the origin of our lab frame, and m2, which is located at distance r2 from the origin of our lab frame. Now we have some point that is the center of rotation. And this point, this origin of rotation, can be accelerating. So we're not going to treat this as a fixed point. It's going to be at position our origin in the lab frame. And with respect to this center of rotation, M1 is located at R1 minus our origin, and M2 is located at position R2 minus our origin. The angular momentum for this system is equal to the sum on I of now Ri minus our origin, so this is the distance from the origin of rotation to each particle, cross their individual momenta. If we were to solve for the torque by taking the derivative, by looking at the rate of change of angular momentum, we find that we get the sum on I of Ri minus our origin cross Mi times Ri double dot minus our origin double dot. And we can split this up into two pieces. The first piece, we're just going to look at the acceleration of the individual particles with respect to the lab frame. So this is the sum on I of Ri minus our origin cross whatever net force is acting on each individual particle, minus the second term is going to look at what happens with the acceleration of the origin of rotation here. And this gives us minus the sum on I of Ri minus our origin cross Mi our origin double dot. You'll notice that this term and this term together combine to give us RCM times the total mass. The net torque on our system is going to be the sum on I of Ri minus R origin cross the net force on each particle minus the mass times RCM minus R origin. So this is a new vector cross the acceleration of the origin of rotation. This is the way we do this in full. However, we can consider some special cases. For all three of these special cases, one is that the origin of rotation happens to be at the center of mass. The other is if the origin of rotation is not accelerating, or if the vector that connects the origin of rotation to the center of mass is parallel to the acceleration of the origin of rotation. Then, in all of these cases, the torque, or the rate of change of angular momentum, is equal to only the term that depends on the external forces. So this is the sum on I of Ri minus R origin cross the net forces acting on each object. Or this is just the total torque is equal to the sum of the torques acting on each of the individual particles. So we can use all of these ideas together to understand angular collisions. Imagine I have some object here that has some center of mass, and I'm going to give it some kick. We'd like to know what happens. In cases where there's no net torque, we know that angular momentum is conserved. This tells us a little bit about what we expect for these collisions. We can look at two different types of collisions. An elastic collision has angular momentum, linear momentum, and total energy conserved. This is similar to a linear elastic collision where linear momentum and energy are conserved. Likewise, we have inelastic collisions where only the angular and linear momenta are conserved and energy is not. So in most of these cases, we imagine there's some sort of impulse that is acting on our system. Impulse, you might recall, is equal to the integral from t initial to t final of some time-dependent force dt. And this is equal to the change in momentum. Equivalently, we've got an angular impulse, so this I've denoted with a subscript theta. This is equal to the integral from t initial to t final of some time-dependent torque dt. And this is going to be equal to the change in angular momentum. We can use these two ideas combined with the conservation conditions in order to solve for the dynamics of a system that has undergone an angular collision. Next week, we're going to look at general rotations. So ones that are completely 3D, where objects might be rotating about two or more axes at the same time and have translational components. Then we're going to introduce the moment of inertia tensor and use that to come up with a more unified description of rotational motion. See you next time. And so if we take, look at, the torque on this object, so this could have mapped the derivative of torque with respect to only the